Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's webinar is ACI 318, 2019 Concrete Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we're located in Philadelphia, Pennsylvania. My colleague Alex Bacon will be your moderator, answering any questions you may have. He's a technical support engineer, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that up at the top with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to give a brief overview of our main finite element analysis program, RFEM, and these concrete add-on modules and the concept behind them and how they work together. Then we'll move into our example within RFEM, and I'll give a quick overview of the model as well as the loading. We'll then run a calculation and review the analysis results, again, still within the main program RFEM. Then we'll move on to the design of the elements, such as the members and the surfaces. I want to first go over some relevant ACI 318, the 2019 was recently added, so how these updates will affect some of the design features within the add-on modules. Then we'll move back to our example where we will do member design within the add-on module RF concrete members, and then slab design within the additional add-on module RF concrete surfaces. So RFEM is our main FEA program. This is where we would fully model the structure, including the materials, the cross sections. We can load the structure and run a full analysis. And these analysis results are going to give us internal forces, deflection, support reactions, so that in the event we wanted to do our own design, we could use that information to do so. But we also have the RF concrete add-on modules embedded within RFEM, and RF concrete consists of a couple different add-on modules. The first is RF concrete members. This will perform an ultimate and serviceability limit state design for 1D member elements, beams, columns. We also can run deflection checks within the add-on module, and of course we can do design according to the ACI 318, the CSA standard, as well as many other international standards. The second add-on module is RF concrete surfaces. So this provides an ultimate and serviceability limit state as well for any type of plate, shell, wall element. Again, this includes the ACI, CSA, and other international standards. So in addition to these two main add-on modules, we have a couple of add-on module extensions. The first is RF concrete deflect. So you have to have RF concrete surfaces in order to run this add-on module extension. This will perform an analytical deflection analysis for our surfaces in either the cracked or uncracked state. We also can consider long-term deflection. RF concrete nonlinear will run a nonlinear calculation in the crack state for both members and surfaces. So this add-on module extension is applicable in both of these. This is for the serviceability limit state only. So we'll actually take a look at the true crack cross-sectional properties and use this for the analysis. Okay, so we can get into our first example today. And you'll notice that I already have my concrete model here for the sake of time. And it consists of a type of podium structure out in front here, and then we have 3 stories over on the left. We have our concrete core consisting of surfaces for our wall elements. We have horizontal slab elements, elevated slabs, of course. concrete columns, and then we also have some beam elements here that we categorize as rib members, which I'll show you in just a minute. So looking at our main FEA program, RFEM, we also have the project navigator over on the left that includes all of our input data. So for example, I can take a look at all of my materials defined. In this case, everything is 4,000 PSI concrete. If we take a look at the cross sections in the program, we have our 12 by 12 columns defined pretty much everywhere. We also have these rib members defined as 10 by 18 cross sections. So we can make additional changes here to our input data within the project navigator as we update this graphically. The project navigator in turn will also update. So just to cover a few of these items within the model that may be a little bit unique, let's take a look at these beam elements here. So notice that these members are dropped down below the slab as supporting members. And I can double click on one of these. The member type here, instead of set to a typical beam type member, which would be a beam or a column, is set to a rib. And when we go into the detail settings of the rib, what makes this a little bit more unique is that, number one, we can drop it below the thickness of the slab automatically. So you'll notice over on the left here, we can position this on the positive local Z side of the axis of the slab. Then we also can set an effective width on either the left or the right side of the member. So we can have this automated at L/6, L/8, or maybe we input that in, which in this case I set this to 1 foot on either side. The program will automatically detect the surface that it should integrate with. So the intent of this is that we can integrate this effective width on the left or right hand side and consider these internal forces for the member design. Once we get into RF concrete members, this is possible. So all of these members over here in this podium type structure on the right are considered rib members. You'll also notice this symbol here between our adjacent surfaces. So I have my 3 surfaces here in the front, and I have my rear surface in the back, and then this symbol here is what's called a line hinge. Now a line hinge can be added over here in our project navigator. We can right click to add a new line hinge, and what I've done here is I've released the moment between these adjacent surfaces. So you'll notice that with a line hinge, we have 4 degrees of freedom. So we have the translation releases, but I want those all to be fully fixed. But I can release the moment about the line's local x-axis. So we're assuming that this isn't one monolithic pour, but rather these 2 slabs are kind of butting up against each other. Translation is transferred between the 2 elements, but we wanted to fully release the moment. So you'll notice that these line hinges are applied along the length of these slabs. So when we are designing according to the ACI or the CSA, we know that an I crack factor should be applied to the flexural stiffness of our members and our surfaces. So if I take a handful of these columns here and I double click, you'll notice that we have the Modify Stiffness tab. And by default, what we would normally see here is the definition type set to none. So when you are designing for concrete, you would want to come in here and modify this to the ACI 318. The program will automatically detect, because of the vertical orientation, that these are columns. Well, we can also see here now that a multiplication factor of 0.7 is applied to the flexural stiffness. So this would be the I cracked factor from table 66311 directly from the standard. Now, same concept for our beam members. If we initially edit this member, we take a look at the Modify Stiffness tab. We just want to change the component type here to beams for a different modification factor of 0.35 for the flexural stiffness. Now, similar to members, when I look at any one of these slab elements, we also have a Modify Stiffness tab. And again, ACI, but the component type is set here to flat plates and flat slabs with a multiplication factor of 0.25. And finally, we have our wall elements with the component type set to walls, uncracked or cracked. So this has been done for every element here within the model, and that is very important if we're designing to one of those standards that we want to take that into consideration. So before moving on to the loading, there's one more element that I'd like to take a look at, and that's the FE mesh, which is incredibly important for any finite element program, that we are correctly setting this mesh size. So under Calculate, FE mesh settings, you'll notice here that the target length of the finite element by default is set to 1 foot. So when I keep these default settings and I can regenerate the FE mesh when I click OK, you notice that quickly solves and we have our FE mesh available to us based on those 1 foot settings. So everything is tied together automatically, including nodes, lines, members, surfaces, walls. Everything is done by the program. So we don't need to do any of those factors manually. But the question is, well, is this mesh too small? Is it too big? Will it produce accurate results? And we have a nice feature here under FE mesh settings that's relatively new within the last few releases called the adaptive mesh refinement. So this is a tool within the program, and I'm actually going to jump back to that PowerPoint to explain this a little bit further. So again, we always have this question in any FEA program: is my mesh too big or is it too small? We know that if we set the mesh to something too big, we're not going to get accurate results because we're only getting results at every FE mesh point. But you set it to something too small, well, sure, your results will be incredibly accurate, but you may be waiting hours, possibly even days, for the model to solve, depending on how big the model is in general. So what we typically recommend is a manual result comparison with FE mesh variation. What this means is we set our mesh to something, we think would work. We run the analysis, we take a look at the results. Well, then we decrease the mesh and we compare our results to the decreased mesh from the larger FE mesh. If our results are changing drastically, then we know that we need to continue decreasing the mesh until we're not really seeing any variation within the results. Now, again, this is a manual process. What this adaptive mesh refinement tool has allowed us to do is to automatically perform this process instead. So the FE mesh is automatically recreated based on the results from the previous calculation step. Now, this is based on the Zinkovich-Zhu method. And essentially, like I said, the program will take a look at the results with one FE mesh settings, and it will compare it to the FE mesh results for something where we have refined it. The max number of iterations by default is set to 1. So this just sets the number of steps during the refinement. Now, typically 1 iteration is fine. You have the ability, though, to consider multiple. The average error tolerance, this sets the error difference between the result comparison. So when we compare the results from one FE mesh to the results from the second FE mesh, what error difference do we want to set that tolerance to? So obviously you can get, you can have the ability to set this error tolerance to something small, and taking a look at this picture over here on the right, this kind of displays the model on the left is going to have a larger error tolerance compared to the model on the right, which has a much smaller error tolerance, and we're getting a much finer FE mesh. So let's go back to our model then today to take a look at this. And like I said, we'll keep the iteration set at 1. I'm going to set my error tolerance to 0.02%. Then we also need to just select any load case that we've created from this dropdown. So you do need to have at least one load defined here. We'll just use our dead load. So when I go to calculate, generate FE mesh, the model looks as though it's almost running in an analysis calculation, but in reality, it's just comparing those results here from one mesh to the other, taking into consideration that error tolerance. So you'll notice that once this is complete, we now have a finer FE mesh, especially where these columns are framing into this 2D surface. We also have a much finer FE mesh where these wall elements are meeting at these corners. So this is a pretty powerful feature if we just want to automatically apply all these mesh refinements. Now, I've given plenty of webinars before where I've manually applied FE mesh refinements to my model. So if you're looking for for more control over that, you would want to manually add these FE mesh refinements, which is available in our Project Navigator. But this is, again, a great feature if we're wanting to quickly refine the FE mesh to have a reliable FE mesh length size to the entire model. Okay, so now that we have completed a quick overview of the modeling of the structure, let's move on to loading. So under my load cases and combinations, you'll notice that I have created just a few load cases here. Now in reality, for a true model, we would probably want to set many more load cases than just this. But for today's example, we have a dead load case, a couple live load cases, a win load case. Now these action categories are important because they set the load factors in our load combinations. And this is according to the IBC, because those are the load combinations that I'm generating for today according to the IBC. So when we take a look at our combination expressions, you'll notice that I have my LRFD load combinations and my ASD, and I can click my little info button here to see directly from the IBC 2018 what those load combinations look like. Most importantly, under the load combinations tab, here are my LRFD load combinations listed in orange and my ASD listed in red. Now all load combinations by default are set to a second order analysis considering P delta effects, which is required by the ACI. So once we are done setting up these load cases and combinations, we would actually apply the loads to our structure. So taking a look at the dead load that's applied, you can see that these are just simple surface loads applied to every level here, 0.05 kips per square foot. Taking a look at the live load, we have added quite a few free loads. So notice that these free loads are applied to only particular sections of these surfaces, not everywhere. We take a look at our second live load case, we kind of have some different arrangement here. So this might be live load considerations that we wouldn't want to consider together, but it's one or the other. So I've set up my load combination so that it's not considering both live loads together, but rather the load combinations will consider live load 1 here or live load 2. And finally, simple lateral load just applied to every diaphragm level here, every story level in the global Y direction. So nothing too complicated. Now we can view our load combinations displayed together, which is going to show our dead load, our live load, and our win load acting on the structure. So now that we are done defining our loads, we are now ready to run our calculation. So I can go to calculate all. For the sake of time, I'm going to pull open a model that I've already run this calculation. It does take just a minute because of some of these additional FE mesh refinements. So what we're presented here are our results once we run our calculation. So the results tab is now available in our Project Navigator. And we can view our global deformations for all of these different load cases and combinations. Now notice you can control the load factors here to decrease this. We have our colored panel within the global deformations. And then we also can smooth the color transition if we want to make this just look a little bit nicer. So deflections are important to make sure we understand, okay, our model is behaving correctly under the applied loads, or did we make a modeling error? Everything looks to be okay for the general deflection. So in addition to our global deformations, we're probably very interested in our internal forces. And we'll start off with the internal forces for our members. And I'll kind of isolate a few columns here by choosing the visibility of the selected objects. And when we look at these columns, we can view the axial loads. So we can see all of these are in compression, as we would expect. We can also view the shear forces in the strong and weak axis direction. We can view the bending moments as well in both directions and so on. Now, all of this information that we're viewing graphically is also available in table format. So we can view table 4.0, the results summary, and we can take a look at the members for the internal forces. All of this information can be exported directly to Microsoft Excel with the click of a button. So this would be Again, important if we're wanting to do our own manual design with our in-house tools or maybe an Excel spreadsheet to export out these internal forces. We can also right-click on a member to visit the results diagram. And the results diagram will just show me in a bit more detail my internal forces, deflections, strains are also available here, what's going on along the entire length of the member. We even can switch load combinations or load cases up at the top. We can export this to Microsoft Excel. We also can add to our printout report. So this really sums up just a basic overview of our member analysis results. Let's take a look at our surfaces. So I'm going to cancel my visibility mode here. And instead of all surfaces, let's isolate to these front surfaces so we'll create a visibility by the selected objects. So we can take a look at the basic internal forces for this member. And again, we have our colored panel here showing us our MX bending internal forces. We also can cycle through these different load combinations, view MY, and these basic internal forces are based on the X, Y, and Z axes, the local axes of our surface. So when I hover over one of these surfaces, we can see here the local axes given to us. When we're looking at the principal internal forces, which is the next available tree here, you'll notice that everything is actually based on these principal axes. And these are going to be the extreme values of the internal forces. So we have M1 and M2, for example, here. Well, axis 1 is based on the max value of our internal forces, and M2 is based on the minimum values. So just a different way to present our results here. Now, of course, we also can view strains. Strains might be interesting for us for concrete design. So everything is visible here. So again, this information is available to us in table format. If we scroll kind of all the way to the right-hand side here within the tables, we can view the strains here, or we can view the internal forces. And this is for every grid point within the surface. So we can export this information to Microsoft Excel, again, if we'd like to do our own manual design. Okay, so the next topic then, after we've covered the analysis, is of course we want to design these members according to the ACI standard. So assuming that we want to take advantage now of our add-on modules within the program. And we can see these add-on modules listed within our project navigator. You can always right-click on an add-on module to make it your favorite, to kind of move it up to the top of the list. Or we can access add-on modules under the design concrete for RF members, or for surfaces, or for members. So before we jump into the actual add-on module, I want to go over several of the 2019 updates that have been considered within the program. And I'll first preface this that this is by no means a complete overview of all the modifications or updates within the 2019 standard that was recently released, nor is it a complete list of everything that was affected within our program. It's just a few that I wanted to highlight on, some major changes that took place. So the first is going to be the reinforcement strain revisions. And according to section 7331 for non-pre-stressed one-way slabs, but also 8331 for two-way slabs and 9331 for beams. Well, the code tells us that these should all be tension-controlled elements according to table 21.2.2. And you'll notice that in figure 2122B from the standard, which I pulled over here, our tension-controlled area within this graph for the strength reduction factors. Well, this now has been modified. This lower limit strain value has been modified according to this section here. So we're now taking into consideration the tensile strain in the extreme layer of the longitudinal reinforcement plus 0.003. Well, previously this value was just a simple 0.004 in the 2014 standard. So This was kind of a major change within this section. Now, this leads to a more economical flexural design for beams and slabs. So we don't have this requirement anymore to add additional tension steel to meet the lower steel strain limit of 0.004, but rather now this is a function of our yield strength of our reinforcement. So what this previously meant was really little, if any, gain to the flexural strength because of the reduced strength reduction factor. So this is obviously going to affect our add-on modules, RF concrete members and surfaces in several ways, but the main change you'll notice initially is that we're going to have a influence on the neutral axis to depth ratio, which you can see in the results within the add-on modules. The next modification or the update was the minimum flexural reinforcement for slabs, and this is section 8611 for two-way slabs. AS min is now 0.0018 times the gross area. So previously in the 2014, this minimum area was based on the reinforcement type and the grade. So now it's just a more simple approach here, just times the gross area. Now this is the same requirement as the temperature and shrinkage, but all the code kind of wants us to do here is to apply this to the tension face of the slab element. Now, how this influences our add-on modules, this purely only affects RF concrete surfaces, and it's going to influence the minimum longitudinal reinforcement. So we'll see those updates within the add-on module there. One-way shear strength provision. So this comes from table 22551. The concrete shear strength, VC, for pre-stressed members has completely new equations here, where we have now introduced the shear area, the minimum shear area. You can see that's in a criteria based on the table taken directly from the standard over here on the right. So this has been completely simplified from the ACI 2014. Now, it should also be noted that if we continue reading in the code, section 225511, we have some provisions here that the concrete shear strength must be less than the equation shown. 225512 has some provisions for the axial load over 6 times the gross area, which is included in these equations, must be less than 5% times the concrete strength. And we've also introduced the size effect modification factor, lambda s. Well, the code tells us that previously, if a member depth doubles, the shear capacity of that member may not necessarily double either. So this size effect modification factor kind of has better control over that rather than just simply doubling the value. So again, the ACI 31814 previously had provisions for the equations for members without an axial force versus members with a compression force versus members with a tension force. So again, much more simplified. Now, I say that it is more simplified, but underneath the hood, what's going on within the program, it's actually quite complex because we have all of these different scenarios, now including the shear reinforcement, which equation to use here, A, B, or C. And of course, we know that this will impact ultimately the concrete shear strength within both add-on modules, RF concrete. I took a little snapshot here over on the right-hand side, just kind of showing a workflow that's essentially going on underneath the hood of how we are calculating the VC value. So this isn't a complete workflow, it's just a nice snapshot, but this just goes to show you all the different scenarios that we have to take into consideration now. The strength reduction factor. So this again refers back to table 2122, which we've already revisited with the reinforcement strain considerations. This just tells us that the moment axial or combined force strength reduction factor for the tension control strain limit is now epsilon ty plus 0.003. So we've already discussed this. Previously we know within the 2014 that this was 0.004. Again, this is just a function now of FYR steel yield strength to consider alternative steel grades other than grade 60. What we'll see here which of course is quite clear, is that this is going to affect the strength reduction factor in both RF concrete surfaces and concrete members. So we'll see a little bit of a different value when we compare to the 2014 there. Serviceability requirements. This comes from table 24235. So there are now revised equations for the effective moment of inertia, I sub E. We can see that from the table over here on the right-hand side, taken again directly from the standard. So previously in the 2014, the equations underestimated the member deflection with low reinforcement ratios, and this was primarily slab elements. And what we'll see now is that this will inevitably affect the deflection calculations in both surfaces and the members add-on module. Okay, so let us go back to our example today then, and let us continue on with the design within these add-on modules. So you'll notice that when I speak of add-on modules, it's nothing more than this dialog box that will come up within the main program RFEM. And we will want to select here now the ACI 318 standard. You'll see the 2014 still available in this drop-down box. We can even click this filters button to show even older standards if we'd like. The strength limit state will be our LRFD load combinations for consideration over on the right-hand side. Our serviceability will be all of our ASD load combinations. We can move over to the right-hand side. Notice we can activate a nonlinear calculation, which will activate that add-on module extension, if we remember way back when from the PowerPoint, for RF concrete nonlinear, but we won't be utilizing that today. Now it's really just as easy as moving down the list here. So we have our materials. 4,000 PSI was brought in from the main program RFEM. We would set our reinforcing steel grade here. We'll use grade 60. The cross sections are also both available to us here. Our 12 by 12 sections, our 10 by 18 sections. Our ribs table is showing us all of these rib elements, if you remember, that are taken into consideration the effective width. So the program has recognized that we've set an effective width of 1 foot. It's also smart enough to know, okay, well, there's no surface on the left-hand side of this member, so we don't really want to consider that. Of course, you'll notice it looks more like an L-shaped beam. But when we look at some of these additional members embedded in the interior here, which you can see it highlighted in red as I click on it within this table, well, it looks more like a T-beam here because we have effective width on both the left and right-hand side. So just reiterating that information because we can design these rib members within RF concrete members. These supports. So what this means is that we can graphically select supports here. And let me cancel this visibility. We'll turn off our results here. And I can select nodes. You'll notice node number 63 and node number 71 if I was designing this rib member out in front here. The supports allow me to define the support width, and in this case, this would be our 12-inch columns that these rib members are framing into. Is it a direct support, or is it framing into the face of this column? Is it a monolithic connection? Is it not? Is it an end support, or is it not? And you'll notice this picture updates automatically over on the right-hand side. The whole intent of this is, number one, we can consider a moment reduction according to 665. This is unchecked by default, but you can take that into consideration. But more importantly, two, we can reduce the shear forces based on a distance D away from the support face according to 9432. So that's the intent of these supports. We won't be designing the ribs for today's example, but just to give you a brief overview. And finally, we have our reinforcement tables. So what this allows us to do is to lay out the reinforcement for our members. We'll begin by giving this one a description, so we'll design just a few columns. Now, rather than designing or applying this reinforcement to all of my members and designing all of them, let's just choose our 4 columns down here at the bottom with maybe a little bit higher axial loads here that we can initially design. So you can see those listed here. We want to define the longitudinal reinforcement. So what I can do here is I can choose a couple reinforcement diameter sizes. Maybe I only want to choose one for the program to select from. And this will essentially optimize here based on the best design setup. The minimum spacing is set to 0.75 inches. The anchorage type is also selected from this drop-down. Notice this picture will update depending on our settings. We will calculate the development lengths as well. The curtailment type, this allows us to define different reinforcement zones. So if we need higher longitudinal reinforcement for bending in some areas of the member but not others, well, we can actually optimize that. No curtailment just means we're going to place the same longitudinal reinforcement throughout the entire length of the member, but we can modify this to different zones if we'd like. The ties and stirrups. So for this, I'm going to select number 4s, for example, from my checkboxes here. We can set the number of legs per section. We can set, once again, the anchorage type here. We also can control the spacing. So similar to the longitudinal reinforcement, we have the ability to use uniform spacing throughout, or we can change these to zone-related spacings. Spacing limits, this is checked by default to consider the maximum stirrup spacing according to the standard, the ACI 2019, or we can manually set the maximum spacings here as well. The reinforcement layer is where I would set my concrete cover, and we'll keep the cover set here just according to table 20.5131 from the standard. 1.5 inches is fine. The reinforcement layout. So this is important because if we were designing a beam, we'd probably want to have top and bottom reinforcement. Well, the program can go ahead and optimize the distribution of that reinforcement. Maybe we want it the same at the top and the bottom. But since we're designing columns, we want to choose uniformly surrounding for biaxial bending, of course. The internal forces we will design the reinforcement for include axial shear, moment, bending, and of course, torsion as well. So we can take into consideration all of those. You can uncheck them if you're not interested in that consideration. The minimum reinforcement, we automatically have this set by default according to the standard. So for both shear and longitudinal, we can also manually set this as well. The ACI 318 tab, well, this is specific to the standard. It just has some additional settings in here, such as the percentage of reinforcement, shear and torsion reinforcement, according to chapter 22, and then of course our strength reduction factors, which come directly from chapter 21. So no modifications to this table here. Serviceability. So this allows us to, first of all, set a limiting value for the allowable crack width. And you'll notice within this drop-down box, we have some suggestions here from the ACI committee on some different allowable crack widths. So for our case today, we'll choose this last one for a dry air protective membrane, 0.016 for both the top and bottom crack width. This first setting here, to design without direct crack width calculation, this just refers to the longitudinal spacing requirements set by the code to limit cracking. So we can leave this checked. The program will optimize that spacing there to make sure it meets those requirements. Design with direct crack width calculation is more of a theoretical approach. We will apply the Gurgley-Lutz equations to actually calculate the crack width. So both of those we can leave checked. Now we also can turn on the deflection checks, and notice we now have a new table available to us, deflection data. We can also activate long-term deflection according to chapter 24.241. This is going to apply a time-dependent factor to our deflections based on the duration of the load here. So now looking at the deflection data, you'll notice all 4 of my members are listed. The reference length, which includes the full member length of 16.5 feet. The pre-camber, we could add that in as well. And then the limiting value we can select from this drop-down, or we can use our own user-defined. So for this option, we'll choose L/360. What I can do is to hit F8 on my keyboard to make that same change to every single cell here as I move down my list. So now my limiting deflection is going to be 0.55 inches. So now we are ready to run a calculation, and you'll notice that this will actually solve very quick. We already have our internal forces from the analysis. All that we're doing is applying these equations from the ACI to determine our reinforcement. You'll notice it does take just a minute though. The program's kind of thinking here, and you can always look at the progress down in the lower left-hand corner. It's calculating the sums and deformations. But point being that the program will essentially take in all that information from the RFEM analysis into this add-on module. So once this calculation is done, what we're going to see here is maybe the required reinforcement by member. So what I can do here is to take a look, and you'll notice that my member, and sorry, this member over here is highlighted probably from when I was in RFEM last, but this member here is highlighted and everything's synced up in the program to the tables within this add-on module. So it's nice to know exactly where you're at within the add-on module. But what we're going to see here is required reinforcement from the analysis. And this is going to include our longitudinal reinforcement, our shear reinforcement, as well as torsion requirements. Okay, so once we have this required reinforcement and the given variables are shown here, we'd like to know what the program's actually designing for this member, and that's under provided reinforcement. So for example, we can take a look at member number 39, and this is the longitudinal reinforcement. The program has come up with 4 number 7s located at the corners here. Same concept for the shear reinforcement. We take a look at the program has designed 53 number 4s at about 4 inches on center. Well, what's nice is we can double click within this picture to be taken to a much larger view of our concrete rendering here. If I want to make any changes to the reinforcement, I can do so directly within this picture. I double click on the 53 number 4s. Maybe we want to change this to number 3s here, and we want to do the spacing as 0.25. Who knows? We click OK. The program automatically updates this picture, and I can exit out of this. When I try and go to a different table, the program says, well, wait a minute, you've made changes to the reinforcement. Let me just recalculate real quick to make sure that you're still meeting all of the requirements. So it does so, and it looks to be that everything is okay. We also have our serviceability check. So remember, we're checking deflections, we're checking the limiting spacings, we're also checking the crack width. And overall, we're seeing for all of our members here, each of these individual checks with an overall ratio of 0.46. So we have our green smiley face because we are below 1.0. So everything looks to be good there. Now, in addition to all of this information, which by the way, we can take a look at here, and we can also take a look at the graphics view. So we are technically within this add-on module RF concrete members. We are just viewing our results graphically here within RFEM. So let me take a look at the visibility by the selected objects, and we can zoom in here. We can view the required longitudinal reinforcement for each one of these members. So you'll kind of notice how this varies along the member length. What else we can overlay on top of this is the provided reinforcement. So what we should always see is the provided reinforcement greater than the required reinforcement, of course. And sure enough, we do at 2.41 inches squared. Now we can view all of this other information as well, such as serviceability for our deflection ratio checks and everything else. So this is all possible to view graphically. We also can turn on the rendering of the reinforcement. So this is just a nice view if we want to see all of these stirrups, our longitudinal reinforcement, our development lengths, kind of extending up into that additional column there. So that is a basic overview of RF concrete members. Now we would like to move into RF concrete surfaces. So what we can do here is to jump to our data tab, and we can launch now. And let me cancel this visibility mode. We'll turn off our results. Let's take a look at RF concrete surfaces. So what's nice about this add-on module is that once you have kind of found your way around RF concrete members, RF concrete surfaces looks almost the same. And this is true for all of our add-on modules. They have the same type of look and feel to them, so each one isn't different. We are going to select the ACI 318-2019 here from our drop-down box. The strength limit state, we can select our LRFD load combinations. We can choose our serviceability limit state as well by choosing our ASD load combinations. And under the detail settings for serviceability, I want to point out that when we go to these edit settings, we have the ability here to activate RF concrete deflect. So this is that add-on module extension we covered in the PowerPoint that is going to allow us to calculate the deflections here for our surfaces. Now this includes long-term deflection with that duration here, where we can take into consideration the time-dependent factor as well. We can turn this off as well. We also have tension stiffening here. Essentially, we know that the reinforcement will take on tension loads. This is clear. But between two cracks, tension stresses are actually transferred into the concrete as well by a bond. So if we wanted to consider that, we can turn this on. Now, you can also visit the help file, which maybe explains this in a little bit more detail, but by default, we'll just go ahead and leave that on. RF concrete nonlinear can also be activated within this add-on module, again for surfaces. So taking a look at the materials, again, 4,000 PSI concrete, reinforcing steel is set to grade 60. I take a look at my surfaces. We have all of our surfaces listed here. This includes all of our walls and our slabs. You'll notice, again, everything is synced up in the background here, which some of these surfaces are a little bit higher than my view. Thickness is shown, but this is essentially where we're going to specify the serviceability checks here for deformation to begin with. So we want to set the limiting deflection, and this can be set as L over 250 based on the minimum boundary line for our measurement of L, the maximum boundary line. Maybe we want a user-defined relative here. In our case, I'm going to choose user-defined absolute. I don't want to see any deflections higher than 0.5 inches, let's say. Now this little info button here is nice because it will just tell you, okay, what does the program mean when it talks about minimum boundary line versus maximum boundary line? Is the deflection related to the undeformed system or the deformed system? And for this, again, this info button has a nice clear explanation of what we mean by this, of the undeformed system versus the deformed. So you can refer to this. For today, we'll be referring this to the undeformed system. Now notice this is applied to all surfaces, but you don't necessarily have to. You can uncheck this and apply to separate surfaces. The limit value of crack widths, this is identical to what we saw within RF concrete members. We can set our limiting value here based on the ACI committee's findings for dry air protective membrane. 0.016 inches is our limiting crack width. We're going to consider longitudinal spacing based on 2432 to limit cracking. We also will use the Gergely-Lutz equations to design with the direct crack width calculation. So moving on to the reinforcement. So the first thing we want to do here is to maybe give it a description. So we'll call this one slabs. And rather than applying to all surfaces, I am going to just design these surfaces out here to begin with. So surfaces 16 through 18. Now the reinforcement ratios, we can see here that the minimum secondary reinforcement by default is set to 20%. So this is the largest longitudinal reinforcement that should be applied. Now all the rest of these reinforcement ratios are based on a cross-sectional area of 1 foot wide within our slab. For example, maximum reinforcement percentage, 9%. Again, this is based on a 1 foot width of our slab. The reinforcement layout. So the first thing to define here is our cover, whether that's to the centroid or to the edge. Let's choose the edge here. And again, referring to table 20.5131 within the ACI, let's set this to 0.75 inches. And notice that you can modify the reinforcement direction as well. It doesn't necessarily have to be along the local x-axis. We can change this at some type of angle as well. The longitudinal reinforcement includes the provided basic reinforcement. So if I know within this slab that I am going to apply at a minimum number 6s at 12 inches on center, we can actually input that in for the basic considerations of the initial analysis. I can import the reinforcement here within my settings, and I can choose a rebar diameter. We know number 6s are 0.75. The rebar spacing will be 12 inches, and we're going to apply this to the top and bottom and in both directions. So when I click OK, the program will automatically calculate this reinforcement area 0.44 inches squared per foot. So again, this is what will be taken into consideration for that initial analysis. Now, the other option you have here is to use the required reinforcement here instead. And all that you need to do is to have the program, or we'll define the diameter here. The program will determine the reinforcement area needed. And that's what it will use for the serviceability analysis as well. So this takes into consideration the required reinforcement from the ultimate limit state. It uses this as the applied reinforcement for the serviceability limit state as well. The additional reinforcement for the serviceability state design. So if the program determines, okay, these number 6s at 12 inches are not adequate, let's go ahead and apply additional reinforcement. Well, what do you want to use for the serviceability design? And your options are available within this drop-down. And my biggest piece of advice to understand what these are is to take a look at this info button. This explains perfectly what you are setting to use for the serviceability limit state design if our reinforcement is not adequate based on this green line here. So we will just leave this as the required additional reinforcement. If we need any additional reinforcement, let's go ahead and use number 6s here with 0.75 inches for our diameter setting. The longitudinal reinforcement to check the shear resistance. You can see the different settings explained pretty well here. What we're going to leave this on as the default is we're going to apply either the greater value resulting from either the required or provided reinforcement in the reinforcement direction for shear resistance check. Now you also can choose one of these other options as well. The ACI 31819, again, specific to this standard, we're going to see here the minimum longitudinal reinforcement for plates according to 7611, 8611 for one-way and two-way slabs. We are going to want to keep that for today to take into consideration those minimums. If we were designing our walls, we'd probably want to uncheck this and check this option instead to use the minimum longitudinal reinforcement for walls according to Chapter 11. Minimum shear reinforcement is according to 763. Shear reinforcement according to table 22551 as well as the strength reduction factors all come directly from the standard. The design method, we're going to choose the optimization of design of internal forces for parts loaded mostly by bending or tension, and we are ready to run our calculation. So for the sake of time, I am going to jump into an already saved model here, and you can notice that it's just taking a minute to load here for these saved results. So let's just give the program 1 minute. Essentially, once again, we are going to take all of the internal forces from the RFEM analysis, but RF concrete surfaces is a little bit more complex with what we're seeing than with RF concrete members. So it does take the program just a minute to calculate those. So jumping to this already saved model, what we will do here is go to the current module since it is selected here from the drop-down. And what we will notice after we've run our calculation is our required reinforcement. And we can view this required reinforcement by surface, for example. And again, everything's kind of synced up here to show us our required longitudinal reinforcement for the top and the bottom and in both directions. This red arrow is showing you exactly where the controlling internal force is. Now, of course, we can't help but notice this red text here that says that the shear is not designable. And when I click into this cell, it tells me the shear resistance cannot be checked because the cross section is entirely cracked. So this is obviously a problem, and we'll get to it in just a minute. Notice we have the required reinforcement here from the calculation. We have our basic reinforcement, which is my number 6 is at 12 inches. And then we have an additional column here that says, okay, well, you still need to provide an additional so many inches squared of reinforcement here in order to meet this required reinforcement. So that's given here. So also notice that we can view this drop-down box according to the ultimate or the serviceability limit state design. When we are in one of these options, ULS, we can click this info button here. This info button will allow me to expand all of the information that went into these calculations. So you can see that it's rather complex with all these different trees. We can view the shear design. We're also going to give you really as much information as we can from the standard, where all the variables are coming from, code references if they're applicable. So this is certainly something if you want to understand a little bit more detail. We also can take a look at any one of the longitudinal reinforcements. We can export this to Microsoft Excel. So again, to really understand where our numbers are coming from. Under the serviceability design, just like what we saw with our members, we can view by surface here our deflection checks, our spacing requirements for our longitudinal reinforcement, and the crack width calculations. And it looks like everything's passing quite well with a max ratio of 0.7, again with our green smiley face. We can click on this little info button to get information for the serviceability as well, and all of the information that went into determining this information. Okay, so once we are done taking a look at the serviceability, let's jump back to the non-designable. Again, this is a problem. So I think what's easiest here is to take a look at our graphics view. And we're currently viewing our results according to RF concrete surfaces graphically. What's nice is we can view the required reinforcement for our longitudinal reinforcement both directions. You'll notice this red arrow is showing us in which directions these are spanning. We're getting in inches squared per foot, these nice contours. Well, under the required reinforcement, we want to view the shear reinforcement. And what we're seeing here is that a majority of this slab is fine. We don't need any shear at all. But the problem is where these 1D member elements are framing into these 2D surfaces. And we zoom in here, we're getting very high concentrations here for our shear reinforcement. And these are the areas that are not colored where the cross section is completely cracked. So we would term this as a singularity. And if we turn off our results, singularities occur because we have this column framing into this surface at this one single FE mesh point. There's absolutely no load distribution based on the true rendered section here. If we look at it, it's a 12 by 12 section. So technically we should get better load distribution than what we're seeing here. But it's an FEA program. This is the same for any FEA program. So we need to instead consider this load distribution in another way. And we'd want to do so with what's called an average region. So in the project navigator, we have the ability to add a new average region by right-clicking on it. And this is exactly as it sounds. We're going to average out the internal forces over a set area. So the first thing I'll do is I will select this surface here, surface number 17. And I'm going to set this to a rectangular section with dimensions 1 foot by 1 foot. So we can consider maybe better load distribution of our 1 foot by 1 foot columns. I'm going to select my average region to be applied to this nodal point. The coordinates are automatically populated here. And we're going to average out internal forces in all directions. I click OK. So now if I zoom in here, I can see my average region applied right to that corner? Well, I can hold down my control key and we can drag and drop and make a copy of this average region. What I need to do here though is to select not only surface 17, but also add surface 18 there. And when I click OK, you'll notice that this average region now considers both surfaces. I'm going to once again make a copy over here this time, and I selected the wrong thing. Let's take our surfaces as surface number 18 as well as 16. And finally, we have one more average region to give, and I will highlight it, hold down my drag and drop, and let's just adjust our surfaces once again. So we'll select just surface number 16 here. So once we're done with these average regions, what we can do here is to take a look at each one of these average regions by holding down my control key, and we have the ability to continue holding down our control key, drag and drop, and make a copy. I'm going to do the exact same thing here. Now notice I don't need to make any modifications to my surfaces because they're still applicable. So I've now applied these average regions at each one of these locations where these columns are framing into my surfaces. And you'll notice that within my results here, I don't necessarily need to take into consideration here rerunning the calculation, because we're not making any modifications to the actual analysis results. We're just kind of smoothing out these high stress points. So when we go back into RF concrete surfaces though, we're going to need to make a couple changes. And we go into, I'm jumping to an already saved model, and there's a reason for that. Is if I go to RF concrete surfaces, and once again, just give it a second to load, under the details setting, if we do not set this checkbox, the program will automatically ignore those average regions. So after we've applied them, we go back into this add-on module. We check on this checkbox to consider average regions for the ULS and SLS design. We need to rerun our calculation, and then we'll be presented with our results here. And now notice, actually, we've improved the shear design. We no longer see that non-designable, but we've also improved the longitudinal reinforcement because we had high stress, high singularity and internal force concentrations at those column locations, even for bending. So this really improved our design quite a bit. Okay, so that really sums up the overall surface design. Now, there's just one more thing I want to mention, which we don't have time for today, but if you go to our website at duluwal.com, and under support and learning, you'll see here knowledge base. And the knowledge base just has all of our technical articles. You can see that there's almost 1,000 of them, really related to the different standards. You can see here timber column design per the CSA standard, as well as just general structural engineering topics. So what I wanted to do here was to search the keyword ACI, and when I hit the search option, the first article that pops up here is design strip consideration. So I wrote this article more recently. It may, the question comes up from time to time, do you consider design strips within the program? And we actually don't take the method of using simple one-way design strips for a reinforcement design for surfaces. But I explained the RF concrete surfaces approach and maybe a couple different considerations for if you wanted to take more of the design strip approach, what can you do within the program? And that's with average regions. I kind of explained the benefits as well as the pros and cons for this option. And probably the more simple application is with result beams. So this can be incredibly helpful. You can even download the model that I used for this article if you're wanting to read more about it and design strips. So certainly refer to that here. Okay, we will conclude our webinar today, And I want to, again, encourage everyone to visit our website for articles such as this, but also just other recorded webinars that I've done in the past that you can rewatch, download models. We also have some online trainings coming up, so if you're interested in those, you can find them on our website. You can register for them. You can even download a 90-day trial version of RFEM, which includes all of our add-on modules. So our contact info is located at the bottom of this page. If you have any questions about any of our products or about today's presentation, feel free to contact us with either the phone number or the email written here, info-us@duluwell.com. This is directly to our Philadelphia office. So we will have many more upcoming webinars. You can register at duluwell.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week or so before these take place, so you can always register directly through the email. PDH certificates will automatically be emailed to all participants today, so you don't need to request them. I will send them out. I typically try and do that within the next day, and these are available for attendees who are here for the full presentation. So this is required by the various states where we are pre-approved providers. You do need to be here for the full 60 minutes in order to receive that PDH. If you watch the presentation with a colleague and you yourself did not register with your own name and your own email, you will need to request that at info-us@duluwell.com. So again, if you did not register with your own name and email, please email us at info-us@duluwell.com. And with that said, I want to thank everyone for attending today, and as always, we hope to see you at our next webinar. Thank you.